Hello everyone, we're the EaglePicher Oracle Capstone Design team, and we would like to demonstrate our work on the Battery Oracle, also known as Battery Machine Learning System, BMLS for short. This project is being led by technical directors Frank Puglia, Director of R&D at EaglePicher, and Christopher Sharon, a former ELECOMP graduate and current software engineer at EaglePicher. The members that make up this team, from left to right, are me, Cameron Emerald, a computer engineering student, Paul Perry, a dual major student in computer engineering and computer science, and Santosh Rajendran, an electrical engineering student. EaglePicher is one of the leading producers in high-tech, state-of-the-art batteries in a wide range of applications. Some of their defining battery achievements are in the production of battery systems for the Apollo 13 and Mars rovers.
Batteries are commonly required to deliver high power and energy while exposed to dynamic conditions and over a long service life. While advancement in battery performance developed at a rapid rate, improvement to the battery management system have consistently lagged behind. The Battery Oracle will lead to advancement in the BMS design, improving the safety and longevity of future batteries. The objective of this project is to develop improved machine learning methods and algorithms to improve performance of lithium-ion battery management system for various battery applications. Anticipated best outcome for this project is to develop the Battery Oracle machine learning system, applying the lessons learned from the AMBATS program to identify performance indicator of lithium-ion batteries for specific use cases. Secondly, demonstrate the application of Battery Oracle methods to empirical data produced on the AMBATS and EagleEye system for fault detection and life optimization. Lastly, in working with the EagleEye team, propose optimization to BMS design for applications such as electric vehicle, direct energy weapon, to improve batteries safety, performance, and longevity, reducing the risk of batteries in more extreme scenario. Summary of team accomplishment includes familiarizing ourselves with the AMBATS platform from the previous year's team, evaluate the AMBATS platform to find noise, conversion from digital twin to Python for ease of use, creation of various tools needed for data process and analysis such as profile generator and p-value statistics tool, started the machine learning process consisting of learning the best model to use and how to use AWS SageMaker.
This project has the potential to have a large impact on the economy, seeing as currently there are no other companies developing a battery management system that utilizes machine learning. If successful, our project will be able to ensure safer, longer-lasting, high-performance lithium-ion batteries, unlike anything else there is on the market currently. The diagram here shows a very simplified overview of the project. Essentially, we are generating data using two different platforms, one being the AMBATS platform from last year, as well as our own digital twin. From there, the data is generated, processed, and ran through machine learning algorithms, which hopefully by the end of this project will result in a battery management system with additional safety and functionality. From here, we're going to be talking about our individual contributions. Cam will start off by showing you what he's been working on.
My main tasks so far were to convert and alter the digital twin for generating data to Python, and to research which machine learning algorithm would be best to use for this project. The digital twin, which was originally an Excel program given to us by Frank, is not ideal when potentially thousands of datasets need to be made, so I converted it to a Python program and implemented a basic UI to change values quickly. Later revisions alter the program to be completely autonomous in generating the datasets for each topic needed. As for machine learning, originally we decided to go with the standard recurrent neural network, or RNN for short, which are able to use data from previous iterations. But due to a problem I found called vanishing gradients, we decided to switch to a long short-term memory neural network, LSTM for short. LSTMs are a variant of RNNs that don't encounter the same problems and can have much higher accuracy when detecting anomalies. Next semester, I plan to build and apply the LSTM model to identify faults against the data created by the digital twin and data gathered on the test platform, and optimize the model to be as accurate as possible. I will be doing this with our next designer, Paul.
This semester, the majority of my efforts were put towards learning machine learning as well as the AWS and SageMaker. I also spent time developing a few small pieces of software to help us better view and understand our data. One of the pieces of software I worked on was a digital analysis tool. Essentially, it's a Python script that enables us to port in data collected from the battery management system or our own digital twin. It does so by turning the data into a CSV file. The data is then processed using a couple of different methods and is then displayed on a dynamic interactable graph. The photo here is an example of a graph that's generated using the tool. Within the software, you are able to configure it to plot a number of different variables against themselves. As far as machine learning goes, my focus this semester was entirely on anomaly detection. I spent time researching and eventually implementing a ML model using LSTM, or long short-term memory, to detect anomalies. Because of the learning curve associated with machine learning in general, our approach was to create a simple model using rudimentary data. The photo here is a graph plotting the anomalies that our model generated. Going forward to next semester, my plan is to continue improving our machine learning model to be able to first detect anomalies on our own digital twin, and then eventually on the battery management system itself. In doing so, my hope is that certain trends will be revealed, allowing us to detect when a cell is in threat of failing, as well as what led it to that point. From there, we plan on using those same trends to build a separate machine learning model capable of optimizing cells. I'm going to now pass the mic to Santush so he can show you guys what he's been working on.
As only electrical engineer in our team, my technical contribution is to optimize performance of hardware to improve data quality. This is important since the quality of data produced from the Embedded platform is used for anomaly detection. To improve data quality, I had to compare real measurement to data produced by the Embedded platform. One of the first tests I did is to see if the resistance values are accurate. To do so, I used 12 lithium-ion batteries to measure internal resistance using battery analyzer tool, and with the same batteries, voltage and current were collected from the BMS to calculate the change in resistance while charging. The results show that the BMS calculated resistance is an average of 77 milliohms, while the measured resistance is at 31 milliohm, thus proving that there is an external resistance captured by the Embedded platform. To locate where the external resistance coming from, voltage at positive and negative terminals of the battery holders were measured with current running through at 1 amps. And the results showed that the external positive terminals are unstable and varying with an average of 39.9 milliohms. The box plot on the right shows comparison between positive and negative terminal resistance. To further prove this, the thermal image on the left shows battery 105, 109, and 110. The positive terminals have higher temperature compared to the negative terminals. The high resistance is caused by the contact between the battery and the battery holder terminals. As you can see, the nominal contact area versus the actual contact area. Lastly, with a 3 amp current passing through, the BMS and the external IR camera capture data on temperature changes. As you can see in the graph how much the BMS and the IR camera catches. This is a more zoomed in version of the graph. The IR camera raises in temperature by 1.2 Celsius while the BMS was constant. The temperature is important since it's a key indicator of when battery is going to fail. Some of my technical accomplishments before May 2023 are to work with the EagleEye team to improve the Embedded platform to reduce noise found from the data collection. Secondly, continue to gather and analyze data from the Embedded platform for the machine learning aspects.
Going into next semester with this project, we plan on continuing to use the data collected from the BMS and the digital twin to further improve the accuracy and functionality of our machine learning models. In addition to this, we plan on collaborating with the EagleEye team to improve the Embedded platform. allowing us to get cleaner and more precise data, as well as working with them to propose optimizations to the BMS for various applications, hopefully resulting in all-around better and safer use of lithium-ion cells. Lastly, I would like to thank our technical directors, Frank and Chris, for providing us with so much support throughout this entire semester, as well as our consulting director, Brendan, for all the help. Also, Professor Jung for allowing us to use his lab and the equipment in it, and last but not least, Dr. Sunak for putting this whole thing together and giving us the opportunity to work on something that really matters.